Hi, my name is R Parlante. I am a Joule Fellow here at the University of Connecticut, summer of 2019. I am a Earth and Physical Science teacher at E.O. Smith High School right here in Storrs, Connecticut. My project this summer is the life cycle of trade wind cumulus clouds. So what is a cumulus cloud? Well, I'm sure you've looked up in the sky many days and seen these puffy white clouds that kind of look like balls of cotton. And they form in the atmosphere very much the same way in which lava lamps move, where warm, heated air at the Earth's surface becomes less dense, rises, cools, and then sinks back down, much like a pot of boiling water. So engineers here at the University of Connecticut have been using computer model simulations to help describe the flow of liquids and gases, as the motions of individual molecules are unpredictable, as are the flows of fluids in general. When studying fluid dynamics, the flow of the fluid can be considered to be laminar, where all parts of the fluid move uniformly together, or turbulent, where the flow of the fluid itself is very unpredictable. We see this often in nature, especially around convection in clouds, sometimes as air moves over islands, and in some cases, we can actually see the same kinds of turbulent motions in the atmospheres of planets like Jupiter. Thanks to my iPhone's time-lapse feature and the right atmospheric conditions, I was able to record these cumulus clouds forming right here from my lab video at the University of Connecticut. As time goes by, you can clearly see the convective motions in the clouds. By using computer code, we can actually simulate the growth of cumulus clouds over time. As you can see, it very much resembles what we expect to see in nature. The same computer code can also simulate buoyancy of air as cumulus clouds forms, where the lighter bluish colors indicate more buoyant air as it rises up into the atmosphere when the clouds form. So why are these studies important? In the age of climate change, where we're trying to better understand how incoming radiation from the sun can be absorbed and kept in our atmosphere, cumulus clouds and their formation is one of the most difficult problems for scientists to understand, specifically where cumulus clouds form, and as they grow, they will reflect more sunlight, actually reducing the temperature of a local area. After some thought, I had to figure out how I would apply this information to my high school science classes. So me and my Joule buddies got together and we came up with some ideas. Because I teach a meteorology course, we came up with a way to use that for my class. By using the MATLAB program, some students and engineers here at UConn have been simulating the motions of fluids, specifically looking at convection. As you can see in the video playing, this is a nice representation of how air would actually move throughout Earth's atmosphere. So after a few days of playing around and seeing what the program could do, a plan was developed to turn it into a lesson. As a result, we created a desktop application from MATLAB as pictured here. Students can manipulate bubbles or thermals of air as they rise through the atmosphere and manipulate certain variables to allow the bubble to form differently. This connects nicely to how clouds actually form in the atmosphere and can serve as a model for their formation. The purpose of this simulation is to use it in conjunction with data we actually collect from weather balloon launch. That retrieved data can be analyzed by the students and compared to how bubbles of air would form in the MATLAB simulation. This should help students better understand cloud formation and growth. As a meteorology teacher, as we start to study how clouds form and properties of the atmosphere, my goal is to use this simulation in conjunction with the weather balloon data to look at a couple specific things. First of all, how temperature changes with height, which is called the lapse rate, and how quickly the balloon is actually ascending through the atmosphere. That should give us a good clue as to how air is actually moving, whether it's moving up, whether it's moving down, and using that in conjunction with video footage to actually observe things that might be occurring in the atmosphere, such as clouds forming at specific heights, a low level versus a high level. In result, this has been a very positive experience. I've had a great mentor and a great Joule buddy, and really look forward to applying what I learned in the Joule Fellow program to my students at E.O. Smith. Thank you.